Hello. So in this video, we're going to be talking about one of our sort of initial sets of derivative laws. And in particular, we're going to be tackling the sum and difference and constant multiple rules. So just like with limits, we want to develop some techniques that'll let us sort of break apart larger functions and expressions into smaller, more manageable pieces. So when we're trying to calculate derivatives, right, it's important to remember that derivatives are just limits of difference quotients. So in particular, our difference quotient here, sort of, the point being, right, that this thing is indeed a limit. This is something that's going to be coming up over and over and over and over and over and over again. So like, we're really going to hammer this in because this is really where almost all of our rules are going to come from. But this is for some f of x in particular. But what if we have more than one function, which, you can think of it as like f of x and g of x, or you can think of it as like multiple terms in, a polynomial. You can treat each of these things as like a monomial for different pieces. So what if we have, for example, the sum of two functions, or the difference of two functions, or 3 times a function, or -7 times a function, right? We don't really want to run through the full difference quotient every single time with this just because now we're multiplying by 3 or something, right? We want to find ways that we can sort of break it up before we start tackling the difference quotient to make it sort of easier on ourselves. So the first one we're going to tackle is the sum and difference rule. And just some forewarning, there is a lot of algebra, but we're going to sort of talk through it. It's not quite as intimidating as it may visually appear. Okay, so determining derivative of f of x plus or minus g of x. So if you haven't seen this symbol before, this symbol is just a stand-in saying that I could use either plus or minus. It's not both of them, it's one or the other, okay? But the sort of idea here is that it doesn't matter which one. That's why we use that symbol. So I'm taking the derivative of f of x plus g of x, or f of x minus g of x, at some specific spot, right? Some x value, which we're calling b. So our first step then, right, is to just sort of put it into our form. So our form is that thing, right, the f of x plus g of x, minus that thing at our point, where we're use b, so f of b plus or minus g of b. So again, if you're not familiar, these symbols, when they show up in the same equation, they basically mean that you're going to use whichever one's on top is sort of the same line. So here, for example, since this one is a plus, that means that one would have to be a plus. Whereas over here, we have a minus plus sign. So that means that if this one is a plus, that one is going to be a minus. Now, as a note, if this is getting confusing, you don't like these plus minus things, run through this thing and just ignore the bottom symbol wherever you see this. So like pretend that's not there. Now it's just a plus. Same here. That's just a plus. That one is just a plus. And this one is a minus, for example. So you can just sort of ignore the bottom symbol and go through this whole thing, and that would be totally fine. Okay. And then if you want, you can do it again by ignoring the top symbol the whole way through. As long as you're systematic in which one, top or bottom, always do the same one, it'll work. Okay. So again, to be clear, going from here to here, all we've done is distribute that negative sign, right? So the f of b becomes negative, and g of b, the sign flips. So if it were a plus, it's going to become a minus, for example. So now, right, next up, what I'm doing here is regrouping the terms. So I put f of b with the f of x, right? And then the g of x is going to go with the g of b, right? And the g of x had a plus minus, g of b had a minus plus, so that's where those symbols come from. Again, if you want, you can just think of it as this one had a plus first, this one had a negative, so that's where a plus and a negative, okay? So now I'm going to be sort of explicitly regrouping, meaning that I'm making clear that I'm thinking of these things together, the f of x and the f of b, and the g of x and the g of b. And I'm doing that because now I'm going to separate them. So the x minus b, right, is a common denominator. So I'm splitting this right on this sign here. Okay. So I now have two pieces. but this is a limit of a sum, right? If you think of it just the top, or the difference, if you think of it as just the bottom. So that means that I can split the limit, right? So in particular, this limit of this first bit here gets the, right, I had a limit of everything, but then I have just the limit of the first thing, plus or minus, which again, if you want to think of it as just plus, and then the limit of that second thing, okay? So this tells me then that I went from this first bit, all of this, down to this last bit. So that's what we're gonna we're gonna skip all of this work in the middle here and just sort of talk about where that works, okay? This tells us then if I'm taking the limit of the plus or minus, then it's the same as the limit of that first thing plus or minus the limit of the second thing. So in particular, since we can split limits over sums and differences, we can do the same thing with derivatives. So even though we had all that sort of work in the middle, what it came down to was the fact that we could split that limit at the very end. And so derivatives also split over sums and differences, just like limits do, okay? So if you didn't sort of track all of that work in the middle, this is the takeaway, that limits split and thus derivatives also split over pluses or minuses. So the next one we're going to look at is the constant multiplier. So if we have some number like 3 or -7 or pi or whatever, some c I'm going to use as the sort of generic letter version, and we're multiplying that against f of x, we want to know sort of how that works. So again, we start with just our sort of classic difference quotient here, right? So c times f of x is our function. So we have that thing at x minus that thing at b all over x minus b. And then all I do here in this first line is, right, pull out that common c from both top terms. But then it's multiplying everything in the top, so I can pull it out of the fraction entirely. And remember that constant multiples can go in and out of limits, so I can pull it out of the limit entirely, right? So I've pulled it out of the limit entirely, but that is just here, the derivative form, right? So this means that this thing is just going to be c times the derivative, which means I can pull the constant multiplier in and out of the limit, which is what lets me do in and out of the derivative, right? So again, it sort of goes through flawlessly. The fact that it works with limits is why it ends up working well with derivatives. Okay, so what do we do? So limit laws, in this case, they translate flawlessly for derivatives. So for sums, differences, and constant multiples, we saw in limits that you can split on sums and differences, and you can pull out common multiples, constant multiples, and so you can do the same thing with derivatives. In particular, you can break up this process of taking derivatives by sort of handling each piece, right? So like we say f of x and g of x thinking of two functions, but most commonly this is used for multiple terms in the same function. So again, if you think of a polynomial, you have all those different terms in a polynomial. This is telling us that we can take derivatives of each term independently instead of trying to like think of the whole polynomial at once, kind of an idea. We also saw, right, constant multipliers. They can be moved freely in and out of derivatives as well, again, because they work with limits, right? It's the same thing for limits, same thing with derivatives. But as sort of looking forward, limits, right, all of this stuff works nicely because the limit laws work nicely. Limit laws work nicely with multiplication and division, with, you know, a little bit of an asterisk there. Turns out this is not going to be the case for derivatives. So derivatives play well when it comes to adding, subtracting, constant multiples. All those things work nicely. When it comes to doing products and quotients, there's going to be a little bit more that we have to tackle. Okay, so that's sort of looking ahead a little bit. All right, so that is that.